Well, hello friends. Today we are going to continue on the JavaScript engine, and we're going to build a garbage collector. So yesterday we started with an AST and we built an interpreter around that, and now the next thing we want to do is we want to be able to allocate objects from a garbage collected heap that knows how to figure out if objects are still alive or not, and then it can reclaim the memory from objects that are no longer live. So obviously a big part of JavaScript is garbage collection, so we need it. Let's just get started. So we'll just start by adding some files like a heap, and I think maybe that's enough to start with. So put that here and refresh. And heap.h. Okay, so how is this going to look? It's going to be a something, and I think we'll see. Let's see who owns this. I guess the interpreter can own it. So let's say that the interpreter has a heap. And let's have an accessor for it so that you can get to it. And yeah, we'll do it that way. Okay, and then we'll just, should probably add it to the forwarding header, but okay, we'll include it here, libjs heap.h. Okay. So interpreter now has a heap, and probably we want heap to know about the interpreter. So we'll do something like that. Okay. Okay. That's cool. And then what do we want to do with this? We want to allocate objects from it, right? So let's look at, we allocated a new function in this super strange way here. Now we're going to want to do this a bit differently. So instead of just doing new function, we're going to ask the heap to create something new for us. So we'll do like heap.allocate. Maybe create, allocate is pretty good. Allocate function, okay. And yeah, that will give us the thing like we did before, and it can just return a raw pointer. Because I think we're gonna do the GC heap with raw pointers, and then make it so that it doesn't matter, that we can still find them when we do garbage collection. We'll see how far we get today, but at least I want to get to the point where we can create some objects and then get rid of the last reference to an object, and then have the garbage collector discover this and throw away the memory for that lost object. So we'll need a helper here to allocate. Allocate, and oh, it's that arguments thing again. Okay. Shit, do I remember it from type name ... args? Is this how you do it? I was just saying in yesterday's video that I gotta memorize the syntax for this variadic template argument thing. So in allocate, what we're gonna do is we're gonna call it like memory is maybe allocate impulse size of t. And we'll have someone here that can just allocate an arbitrary amount of memory. And we should probably get act types. All right. And then we want to construct the t in that memory. And we want want to forward the args to it. Am I doing this right? Damn, okay, I can't tell if I'm doing it right or not. Probably not. Unexpected parameter. Okay, hold on while I cheat. I'm getting close to remembering it. I forgot to ... here. Alright. Well, we'll get them. Next time, maybe. And then finally, we'll just return that memory as a t-star. Okay. Now what we need is a way to allocate some memory. And I think that we're going to organize our memory into blocks because it'll just make it easier if you have like a whole bunch of garbage collected objects. What should we call them? GC allocated objects? If you have a whole bunch of GC allocated objects, it's really nice if they're all next to each other in memory, because when you want to visit all of them to see what's in there and determine if they're alive, then it's good if you don't have to go all over memory, but you can just iterate over a tightly packed area. So let's invent the heap block. And maybe they can have a static size. How about 16 kilobytes? How about we call it block size? All right. And maybe they should have a, so we're going to chunk these up into little chunks or cells, maybe. Like a prison block has prison cells. So I think we'll call them something like that. Explicit. All right. And actually, let's put this out of line. We'll keep it like that. And we'll keep the cell size here. We're going to assign that right away in the constructor. Well, let's just use an initializer anyway. It's just a good habit, honestly. And then we want to have our storage, essentially. And the size, so these blocks are always going to be 16K. And then the storage is an array of cells. And how many cells we have depends on the cell size. So the cell count is the block size minus the size of the block itself, like this little header that we're looking at right now. Divided by cell size. I think that makes sense. And then maybe we can have a getter for the cell size, just to be nice. And maybe we should even have a way to get a cell. And we'll figure out what a cell is momentarily, but we'll start with finding our way to one. So that would be like, I guess, reinterpret cast cell m storage index times cell size. Okay, and then we just need to come up with what a cell is, and I think maybe it will be something like so a cell is going to be the like this chunk of a heap block, right? And I think we'll make our object class inherit from cell so that he can just fit into one. So if we look here, we defined this, or we declared this object thingy, and we can just say that you are a cell. And maybe we should make that its own header, actually. cell.h. All right. So okay, so what goes in a cell? We need a mark bit, because we're going to do a mark and sweep garbage collector here, just a basic one. So we're going to need a mark bit and probably like a live bit, something that tells us if this cell has like a live something in it or not, right? And that's how we'll know if we should bother destroying it or not. So how do we do this? Like a mark bit, false, and a live bit, say true. And let's see, it is marked. Set marked. I don't know. B. All right. Ooh. Okay, these are very exciting. Okay. And of course, we want these to be virtual. So virtual cell. Should probably also have a class name overrideable thing here, because we already have it down here. Now this guy just overrides what's in cell, and this will allow us to print out for any live cell, what kind of cell are you? Which will be very interesting, I think, when we're debugging this, which we might have to do a lot of, but we'll see. Okay, so that's our cell. Now, in order to mark effectively, we're going to need to visit the entire object graph, right? So in JavaScript, if you have one object that points to another object, whether it's like explicitly set up that way or if it's implicit through the engine implementation, we need to make sure that something doesn't die if we depend on it, right? So we got to make sure we visit the whole object graph here. And to do that, we'll have something like visit graph that takes a visitor, something like this. And maybe it's okay to not implement that. We'll say call it cell visitor. Maybe we can even put that in here. So like struct cell visitor or class cell visitor. Class with public still looks so much better than struct for some reason. I don't know why. So we'll have virtual void visit. And you can tell him that you have visited a cell. Something like that. And then this is how we will visit the whole graph. So an object, for example, so a JavaScript object has a set of properties, right? And these properties can be other JavaScript objects. So we need to actually implement this here. Visit graph, and then an object we'll do visit graph, say visitor, visitor, visit for auto IT properties. Okay, so visitor dot visit visitor dot visit IT value. I guess we need to check actually if that is a visitable. So if IT value is an object, then visit it. Cannot initialize as a const. Okay, we'll just paper over it for now. Const cast. Oh, can't const cast and change the type in the same cast there. Makes sense. Okay, so then of course it's up to the whoever implements the cell visitor to do something useful with this. But maybe we shouldn't call visit like this, but rather visitor IT value as object visit graph visitor. Yeah, then we'll just recurse. And then it's not up to the visitor to accumulate things and then eventually visit them. It might be a little nicer on the stack to just accumulate things in the cell visitor thingy, but well, I'm getting ahead of myself. So we'll just visit the whole graph, and of course we'll also do whatever the default thing to do is. We'll call that first, and maybe actually the default thing should be visitor did visit this. Something like that. That's pretty good. Okay. Right. And visit, yeah, because visit was a weird name. Did visit is better. And I can't call that because it's const. Oh, because this is const. Oh, why did I make it const? I'm not sure. Let's not have it be const. It's just going to confuse things. Even though it's kind of sort of logically const because you're just discovering the graph, but okay. So in our heap now, we have this cell. Oh, I'm going to open that up again because otherwise I'll forget what it looks like. Okay, so this is the cell. It has a class name, a visit graph helper, and mark and live bits. Okay, so in the heap block, we'll need something like template, type name, callback. For each cell, and here we can just iterate from 0 to cell count plus I, callback cell I. Okay. Good. Now, I guess this thing here can return a cell instead, because then, yeah, and then we can actually static cast. Slightly nicer. So let's see about implementing this heap thing. So heap, allocate, impl. Forgot the name spec. Okay. So this guy. Impl. We can also just call it allocate cell, actually. Maybe that's a little bit nicer since that's what we're doing. Okay, so we want to find a heap block that has a cell in it and then allocate a cell from that heap block and return it. So we need to store our heap block somewhere. Vector own putter to heap block. That's simple. Seems like we need to include some things. Okay, and then we will just iterate over our blocks and try to allocate. So cell is block allocate, or no, hold on. If block cell size is greater than, if size is greater than block cell size, continue. Yeah, we'll just do a first fit. So block allocate like that. If return cell, okay. And then if we exit this loop, this means that we didn't find one. So then we'll need to create a new block. So heap block, malloc heap block size. And we create a new heap block in that memory. Okay, I'm writing this backwards today, second time. And we just need to provide the cell size. We'll just use the size. This is going to create like one new heap block. Anytime you allocate a new size that we hadn't seen before, we'll make a new heap block for just that size. And obviously, this is not perfect, right? We're going to want to collect sizes that are kind of similar and use the same block. But right now, this is going to be good enough just to get started. So I guess we can just call it block allocate m blocks append. Oh, how do we add? We need to instantiate a non-null own putter. Non-null own putter. Own putter adopt block. I think maybe I have to be a little more specializing. Block. That's still not good enough. Maybe I did. I think maybe it doesn't see the template. No matching constructor. How do you make these? We need to call this constructor here non-null own putter. Oh shit, right, it takes a t-amp, so we need to dereference it. There we go. Okay, and then we can simply return block allocate. And block allocate needs to have an implementation. So we'll call it allocate, yeah, like that, I guess. And we can, maybe we should put these in separate files. I don't know why I wanted them all in heap.h. Heap block. Okay, refresh, heap. Okay, let's just take that out. Heap block. And maybe we need, we're probably going to need cell for this, so we'll just include it. Okay, so that's our heap block now in his very own file. include libjs heap block. Okay. So the thing we wanted to implement now is heap block allocate. And ideally, this would just pop something off of a free list. So let's imagine that we have a free list, which will just be a linked list of available cells in this block. So if we don't have one, return null putter. Otherwise, let's see, where's heap block? Okay, I'm gonna forward declare some things here. Okay, heap block. Okay, so we need a free list. This would be like a free list entry. Free list. And this can look like, I guess, like a cell, and so we're never going to actually allocate a free list entry or instantiate it. We're just going to use this type to sort of dereference each cell if it is in the free list. So we're going to do the free list inline in the block. So every cell in the block that's not currently used, it will be in the free list instead. And the free list will just be a linked list that's laid out inside of the block. So it's made up of all the unused cells and sort of pointing to each other. And then we can just pop one off of the front when we need to allocate. It'll be very, very fast and simple. So here we just need a pointer to the next, really. Okay. So what we'll do is cell is exchange the free list with the next in the free list. Maybe we can even return it that way. Does that make sense? So this will return the free list and also assign free list next to the free list. Pretty good. Okay, I think that will be good. And of course we need to actually build a free list, so let's do that in the constructor. Size cell size. And we can just iterate from 0 to the cell count. And what do we say? If I is the very last cell, then let's see, free list entry is free list entry, cell at I. The very last thing is not going to have a next, so that's when we run out of possible cells to allocate in this block. It will be full. And then if it's not the last one, we'll just say that free list entry next is free list entry cell I+1. So each one will point to the next one. And then we start at the free list pointing at the very first cell. So there we go. Maybe I should be a good boy and static cast these. Wouldn't that be nice? Collecting those good boy points. I should be better about using static cast anyway. Okay, so I think that's our free list, and we have our allocate function, and we have our new func, and we have a new object somewhere else. these look so weird, right? So here, we'll just do heap allocate object. Okay, now it's starting to look a little bit less weird. It's still going to be a raw pointer, but I'm thinking we can get to a place where raw pointers are okay if the thing that they're pointing to is managed by the GC heap. But it's going to take some time to get there, but we'll get there. My nose is so itchy today. Let's see. So, what do we want to do now? I guess we could start to think about collection. So here's our little test program that we made last time. If you recall, what this program does is essentially function foo, return 1 plus 2, foo. This is the program that you see here. I just made up the AST like this. So this puts the current implementation will put the foo into the global object as a function object, and that means that we have a global object on the heap now, and inside of it we should find a function object with the name foo. So I think one thing that would be interesting is to just do a garbage collection on exit and see what we discover. So I'm going to make a function called GC. Or should we call it collect garbage, maybe? It's a bit more Serenity-like. Collect garbage. That's pretty good. Okay, so how on earth are we going to do this? Well, I have seen garbage collectors before, so I know sort of what they do. Incomplete type heap block, let's just fix that. So basically we want to do, first we want to find all of the possible graph roots that we can and just collect those. So anything that is known to point anywhere in the GC heap, we want to find it. And then we want to, for anything that's a cell, then we want to go from that cell to all of its children and their children and so on, like visit the whole graph starting at those roots. So step 1 will be collect roots, and then we want to clear all mark bits, and then we want to mark live objects. Wait, hold on. We don't want to do that. After we collect the roots, we want to visit all live cells, starting at the roots. Visit live cells. Yeah. Clear all mark bits, mark live objects. We can say mark live cells, actually. And then we want to sweep dead cells. And that's where we'll deallocate things. This seems like a pretty reasonable plan. So let's see, collect roots. Let's just do this like it looks like very nice like this, right? Like you just see the steps. So let's try to keep it like that as much as possible. Collect roots. Maybe like we're gonna need some state. So it won't be quite this perfect, actually. Our roots are going to be a hash table of cells. roots, and then visit live cells starting at roots. Clear all mark bits. These just have to go through all of the blocks and do stuff. All right. Hash table, so this would be all live cells. These are just the roots. Okay, so visit live cells. We'll visit all the roots, starting from all the roots, collect the live cells into the live cells hash table. Okay. And then we'll clear all the mark bits, doesn't need any inputs, mark all the live cells, and sweep all the dead cells. I don't think that needs any inputs either. Okay. So this one can look like this, and visit live cells can be like this. And clear all mark bits can be like this. Okay, and finally sweep dead cells. So pretty good. Okay, so let's just declare those, make them all private here. Okay. Oh, and we need hash table. Okay, so collecting the roots. Let's see. Right now, we only have one known root, really, which is the global object. So, this nose thing is so irritating. What did I do to my nose? I was eating so much pepper today. Perhaps not the best choice. So we have the global object. We need to actually, okay, global object. So that's, I guess that's our only known root at the moment. It's an object. I cannot do that because it's an incomplete type. Well, I'm sorry. I forgot that you also need that. Okay, I think these are all of our roots. When we add more things, we'll need to add more roots here, but so far so simple. And then now that we have the roots, we can visit all of their graphs. So let's see, for auto root in roots, we'll need to make a, we need that visitor thing. So class liveness visitor is a public cell visitor. Wait, why did I call it cell visitor like that? That's so weird. I can just call it visitor. Virtual and liveness visitor. And we want this guy to operate on this. We'll just give him a reference to the cells hash table. Live cells. And then this virtual can just put them right in there. And live cells set cell. See? Now we will visit all of the things. For everything that we visit in the object graph will now just be added to this hash table. And of course, it doesn't accumulate any duplicates because it is a regular, what is it called? Like a regular hash table where duplicates are sort of consolidated into a single entry. So that's good. Okay, so we'll collect all of the live cells if we just make a liveness visitor for the live cells table and visitor root. Wait, what do we do? Visit graph, right? This makes sense, right? So we have a visitor and we'll just send him out on an adventure here, and we don't know how long it will take, but he'll eventually come back to us having stashed everything he found into this hash table. I think then we can just return. And then now that we know, now we have a comprehensive hash table that contains a pointer to every object, every cell that's known to be live right now, or known to be reachable from any other place that we care about. So now we got to clear all the mark bits. So we'll just go through all of the blocks. And we'll do for each cell. This is a little awkward, but I think we'll do it here for now. But it might be nice to not have to visit every cell to do this, but we don't have to optimize everything right away. So we'll just say cell set. I feel like I added something for that. Set marked false. Okay, so this step just removes all the mark bits, and then in mark live cells, we iterate over all of the cells again. M blocks block for each cell. And this time, if live cells contains cell set marked true. Okay. At this point, only the reachable cells are going to be marked. Then we just have to go through the blocks one more time. In the last and final phase, for each cell. And here we will simply check if cell is live, but it is not marked. Then, dude, we are going to take that back. So, do block deallocate cell. How about that? Does that work? What's this? Oh yeah, didn't define. Did not declare. So we just call it deallocate on the cell and then be on our way. That makes sense to me. Well, let's see how we would implement that. So we would have void deallocate cell heap block. Okay, so the companion here, heap block deallocate. Of course, this doesn't do any sanity checking that the pointer is actually inside of this block and stuff like that. Those are things that we should add, but in the interest of just staying focused, we're just going to power forward. So let's see. So I guess we want to call the destructor, right? So call the destructor on the cell. Oh, we can add a little bit of assertion. Actually, I shouldn't be so. I should assert that it's not marked. And we should assert that it is live, because it's about to become non-live. Okay, so now we have run the destructor on this guy. I noticed that we did not run the constructor here, but we did that in the allocate helper, right? Yes, this is where we run the constructor. Okay, that's good. So in deallocate, we run the destructor, and then we want to turn this into a freelist entry. So just reinterpret cast it to a, I suppose we could actually static cast it to a freelist entry. Okay, freelist entry. Next is the previous head of the freelist. So we'll just put it back in the front. And and then the freelist becomes the freelist entry. Right. Is it really this simple? I feel like this is vaguely good. So, did we think of everything? I'm not sure. So I guess we should log something when we do this. So let's dump out the roots that we found. Roots. And maybe we can put this in some if-defs. Heap debug. So you'll have a way to turn this off later, but we're going to need it now for sure. So root. Oh, how should we print this? Something like this maybe. And then we'll add a log stream thingy for this. So cell. Maybe this could be forward declared. Can you forward declare that? Yeah, that's still good. Okay, great. We don't have a cell CPP though, but we could have one. We're doing pretty good on the not compiling front, I feel like. Just building like madmen, but it's all good. So cell CPP. Cell, all right. So this is just to pretty print a cell. If cell is, I don't know, string cell class name, we'll just do something like this. Does that work? Oh no, I need to include log string finally. Okay, so yeah, the debug logging output will just be the class name of the cell and then these curly braces. All pass through this function will call itself. Oh shit, right, because I'm throwing him a cell. So we should probably do it this way. Although I don't love the idea of passing cells around by reference so much, because it's going to get really confusing. So maybe we'll do it like that. And maybe I'll collect one good boy point more and use static cast. Okay. And maybe I shouldn't dereference the pointer if it's null. So if no cell. Cell, null pair. Yeah. Okay. Then we can dump out the roots like this. Maybe we'll say roots collected. Collect roots. Yeah. Just do something like that. Bloop. Nice and fancy. Okay, and then let's dump out all of the live cells that we found. Visit live cells. I'll use an @ sign here instead because it will be cute. Live cells. And let me clear the mark bits. It's not terribly interesting. Marking the live cells, that's a bit more interesting. So let's say mark live cells, and I needed this guy. So, okay. So now we can see which ones are getting marked, and then we can see which ones are getting swept. I think we'll use the international destructor symbol for that. Sweep that cells. Okay, are we ready to compile? I am feeling spicy. Let's try it. Userline.js, sync, and run. Yeah. Well, it wasn't going to compile on the first try. Come on. Cell visitor. I forgot to rename that. Cell visitor. What is this? There's an incomplete type heap block in presumably this constructor right here. That makes sense. I can put you out of line, sir, don't worry. Heap, interpreter, M. No big deal. Sorry you had to wait. And now I have a incomplete types in my hash map in what? An object or what? In heap CPP. Wait, what's incomplete? The property hash map has an incomplete type. In what? Object.h? This value. Okay, well, I'm going to put those out of line anyway, because Now things are starting to get a little bit more complex here, so moving things out of line is going to help us retain decent compile times for a while, which is always nice. So there. Another incomplete type. I guess I should move the heap destructor into the heap CPP as well. Let's just make sure that we don't cause any weird incidents. Okay, and oh, did I forget to add heap block to the make file, perhaps? Yes, I did. Oh, and we have built. So I bet you it's gonna crash, but we'll see. And we crashed. All right. So what did we do? We collected the roots. We found one root, presumably the global object, and we visited the live cells. We found the global object here and the function object, the foo function. And then we are setting the mark bit on both of these guys because they're both still reachable, if that's true. And then sweep dead cells. We are trying to sweep an invalid address. And it looks like it might be uninitialized malloc memory. Well, well, well. Did we forget to... I think when we create the free list here, we need to actually say for each one that it is not live, because all cells will start out in live true, so that when you instantiate something that inherits from cell, then it will be live. And it's only when we construct a free list and we'll say that it's not live. And then deallocate should make it not live again, and it doesn't do that currently, so we'll do that here as well. Set live false. So notice how the memory actually is not fully deallocated, right? We're still keeping the heap block. We're just calling the destructor on whatever was in the cell, and then put the cell back in the free list, and we also mark it as not live. It's pretty good. Pretty good. So let's see what else. Okay, now we ran to completion. And of course there was nothing dead to sweep because we don't have any garbage. That's fine. So let's create some garbage. What if we just make some garbage? What would happen? Heap, allocate. We'll just make an object. JS object. So because nobody is going to claim this, it won't be part of anyone's graph, and it won't be a known root. It should show up as garbage. And indeed, we can see here that we are sweeping one dead cell with an object in it. That's pretty cool. That's pretty cool. And this output turned out really nice too. It's really readable. Awesome. So I wonder what happens if we say that we do like one GC pass like this, right? Like GC on exit. And then, wait, collecting garbage. And then let's overwrite that function thingy in the global object. So we'll just mess with him and we'll like replace him with something else. Interpreter global object put foo, and now we'll put some stupid value there, like JS value 1, 2, 3. We'll put the number 1, 2, 3 in place of the function, and then we'll collect garbage again. Collecting garbage after overriding global object.foo. Now the second pass should discover that the foo function is no longer reachable, and it should reclaim that memory. Okay, did it work? Collecting garbage. We're sweeping that stupid object we made up, and then after we overwrite global foo, then look at that. It gets swept up. That is really nice. Very cool. That's it's really nice that it just seems to work. Of course, I'm sure that I just made some bugs and some stupid decisions and whatever, but it's a pretty good start, you have to admit. Maybe I'll leave that comment in there so we can see what this program actually is. It's a little easier to read until we have a lexer and parser. But now we have a garbage collector, so that's awesome. Oh man, I wrote a lot of code there. Okay, let's commit this, I guess. So this is really gonna have to be one big commit anyway, because it's all interdependent. Lib.js. Oh, and we need to add the copyright headers once again. So, come here, cell. This is pretty cool, though. I'm really happy with the progress here so far. I guess I was expecting a little bit more trouble here, but I guess I did have a pretty good idea of how mark and sweep works in theory, which helps a lot. So let's see, what else did I add? I guess those are all the new files. Node.js. Git commit. Node.js. Or you know what? We can do everything except the JS test program, and then we'll commit him separately. Add a basic mark and sweep garbage collector. Objects can now be allocated via the interpreter's heap. And objects that are allocated in this way will need to be provably reachable from at least one of the known object graph roots. The roots are currently determined by heap collect roots. Yeah. Anything that wants to be anything that wants to be collectible garbage should inherit from JS. So JS. So we'll just call it cell. The fundamental atom of the GC heap. Yeah, I mean, there's a million things you can say about it, but I think that this turned out really, really clean and simple. So hopefully everyone was able to understand how this works. And if you're struggling with it, then just look at the code in its finished state, and I think you'll probably find it maybe a little bit easier, because I really like how it ended up with this here. Like, this is so nice. I wish I would write. I should write more programs in this style, where you're like, you want to do something and you break it down into parts, and then you call one step at a time. Anyway, this is pretty neat. I'm really going all out with the correct smiley faces, but let me show you a little bonus content. Because I was tweeting the other day that the first 10,000 lines of code of Serenity I wrote on a Slackware 11 machine from 2006. It was just the only machine I had access to at the time in 2018. And I downloaded Slackware 11 for it just because it was like era appropriate. And in the release notes for this, it ends with "have fun." And that's why I started using this, because he told me to have fun, Patrick Folkerding, so I've been having fun since then. It's a little backstory. Anyway, I think that's going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out while we implement a simple but seemingly functional garbage collector. Of course, we're going to need to start using this and doing stuff with it, but I think a decent foundation has been laid, or however you say that. Cool. Yeah. So, what do I say next? Thanks for hanging out. I hope you saw something interesting. And check me out on Patreon if you haven't, and GitHub sponsors if you like that kind of thing. I have links to everything like that in the description below. And I will see you next time. Bye.